Hello! Welcome to this lecture on normal distributions or normal curves. After today, students should be able to explain the importance and use of the normal distribution, describe the properties of the normal distribution, transform raw scores to z-scores and vice versa, transform a z-score into a proportion or percentage and vice versa, and calculate and interpret the percentile rank of a score. So what is a normal distribution? Well, the normal distribution is a theoretical bell-shaped frequency distribution. So it's not something that actually exists in reality, but it is something that exists in theory. We do have some distributions, some variables that begin to approximate this normal curve, but something that looks exactly like this normal curve shown here does not really exist in reality. It is perfectly symmetrical such that this midpoint here, highlighted in red, this midpoint is the highest frequency. So it is the mean, median, and mode of whatever distribution or variable we are talking about. So that means if we have a distribution that is normal, then we have the mean, median, mode all in the same spot, all at this point of highest frequency. So this would be the most common category in our data set, hence the mode, but it is also the middle case or middle value for this frequency, so it's also the median, and it is the average for this distribution or this variable. And so the midpoint here is going to be our mean, median, and mode, and then we're going to have it evenly divide our distribution such that 50% of the cases are on the right of this midline and 50% of all the cases are on the left. What this means is that the area under the normal curve is going to equal 100%. Again, with 50% of those observations falling below the midline, so that left side, and 50% above on the right. The area to the right of the midline are cases that fall above the mean, median, and mode. So the cases that are higher. So you're above average, above the median, above the mode. And the cases to the left again are going to be those that are below average or below the mean, median, and mode. Furthermore, we can use this normal distribution to see what percentage of cases fall 1, 2, or 3 or more standard deviations above or below the mean. So going back to the previous lecture where we discussed the standard deviation, we can use the standard deviation to create a standardized value for each value in our distribution. So we can take those raw scores from whatever we're looking at, whether it's SAT scores, whether it's GPA, whether it's income, whatever it is, and we can use the standard deviation and the mean from that data set, that distribution, to calculate standard deviations above or below said mean and allow us to get an idea of how far above or how far below the mean a certain value is. And so this graph gives you an idea of what percentage of cases fall within a standard deviation. This mu here is the mean, median, and mode. This is the midpoint line. And we can see that 34.1% of cases fall between our midpoint and one standard deviation above, and 34.1% of cases fall one standard deviation below. And we can see if we go up to 2 standard deviations, we could add 34.1 plus 13.6 to see how many cases fall between our midline, our mean here, and 2 standard deviations above the mean, and we would get 47.7. And we can keep going. We can see that if you are at the 2 standard deviations above the mean in whatever variable we're talking about, then there's only going to be 2.2% of cases that are going to be higher than yours. You have only maybe 2% of cases that are above yours. And in contrast, that means that there's going to be about 97.8% of cases that fall below that second standard deviation. So what this allows us to do is see where a particular score or particular value in a distribution is relative to all the other values in the distribution. How far above the mean, below the mean, how does it compare to other values in that distribution? Here we have another graph, and we can see that, again, if we want to see what percentage of cases fall within one standard deviation of the mean, we can see that it's here at 68.2% fall within one standard deviation of the mean, 95.4% of cases fall within two standard deviations of the mean, and 99.7% of cases fall within three standard deviations of the mean. And so this graphically shows you how we can use this. So now that we have some examples of these normal distributions and normal curves, let's talk about how we can interpret and use this standard deviation and normal curve. The symmetry and fixed nature of the normal curve allows us to determine the proportion or percentage of cases that fall between any score and the mean, or any two scores. So we can actually compare how many cases fall between your score and your friends. How much higher is your score than your friends? Things like that. So the first thing we have to do is convert the raw scores that we have, whether from SATs, income, whatever it is. We need to convert those to what are called z-scores. These are the standardized units. Z-scores are the number of standard deviation units that a given raw score is above or below the mean. So going back to our previous graph, we had stuff that was 1, 2, 3, or 4 standard deviations above or below the mean. That is a z-score. And what we can do is take a raw score and convert it to a z-score and see where it falls on that normal distribution. This requires that our variable has a distribution that approaches normal. So this does not work if we have a distribution of cases, or a variable whose distribution does not approach normal. We also need to know the mean and standard deviation for that variable. So when we're calculating that z-score, this is the formula we're going to use. The z-score is going to be equal to y minus y bar over s, where z is the z-score we're trying to calculate, y is the raw score we're trying to standardize. So y is that individual raw score that you or your friend have in our example previously, and y bar is the mean or average for that distribution. Finally, s is the standard deviation. So we're going to take that raw score, we're going to subtract the average, and we're going to divide that by the standard deviation. So let's practice this on an example. So let's look at SAT math scores. The mean for SAT math scores has a mean of 531, a standard deviation of 114. We're assuming that a frequency distribution of the SAT math scores is very close to the normal curve. So we're going to make that assumption that this is at least approximating a normal curve. We may be wrong, but we're going to make that assumption for this example. And so we want to know the z-score for a math score of 634. So we have a mean of 531, a raw score of 634, and a standard deviation of 114. And we're again going to use that formula of the z-score is equal to y minus y bar over s. And so we're going to take y and we're going to substitute 634. We're going to subtract the mean of 531 here, and then we're going to divide by 114. And what we end up with is a z-score of 0.9. So what we can say is that a math score of 634 is 0.9 standard deviations above the mean. Furthermore, we can use this z-score and the standard normal table, which I'll show you in a moment, to find the percentage of cases that fall between our SAT math score and the mean, above our score, as well as below our score. So this is where our 0.9 would fall in our normal distribution. And if we wanted to look at the percent of cases that fall between our z-score here of 0.9 and our mean, we would get 0.316 or 31.6% of cases. So 31.6% of cases fall between our raw score here, or our standard score here, 0.9, and the mean. Next, we can see that we have 0.184 or 18.4% of cases that fall above our score. So again, this is about 18.4% of cases are going to be above ours in the distribution. Finally, let me erase that. We can see that our score is higher than 81.6% of cases. And how I got this value is I took our 0.316 here and I added 0.5 because we know that this middle line here bisects our graph, and that 50% of cases are going to fall below that line. Since our value is above that line, we know that we're going to have 50% of cases that we're going to be higher in, plus this 31.6. And so we get a score here of 0.9 that is higher than 81.6% of cases. Alright, so how did I get those values? How did I get that 31.6 and that 18.4? Well, we can look at Appendix B in your book, and we can see what is called the standard normal table. And the standard normal table has 3 columns. The first is this A, which is the z-score. The second is B, which is the area between the mean and the z-score. And the third is C, area beyond z. And so we go down, when we have calculated our z-score, we can go down column A and find our z-score. We can find it here at 0.9. I've circled it for us. And we can see that the area between the mean, that midline in that distribution, and our z-score is 31.59. I rounded to 31.6, or 0.3159, rounding to 0.316. We can also see that the area beyond z, this is the proportion or percentage of cases that are above our z-score, is 0.1841. Again, I rounded to 0.184, or 18.4%. And so, again, graphically, this is what it looks like. Here's our 18.4% highlighted in green. Our 31.6%, or 0.316, is between this midline here and our score. And if we wanted to know the total percentage of scores that are below ours, we just have to add that 50% from the cases that are below this midline. Alright, some things to keep in mind here. The properties of a normal curve are such that the mean will always have a z-score of 0. This is because if we took our mean of 531 as our raw score, and we subtracted the mean of 531 and divided by our standard deviation of 114, we're going to get 531 minus 531, 0, divided by 114, which is still going to be 0. So the mean for a z-score will always be 0. And a standard normal curve will have a mean of 0 and a standard deviation of 1, always. So even if we're talking about different variables, if we've standardized the values for that variable, we've converted them to z-scores, that means that the mean will be 0 and the standard deviation of 1 will always be true for that normal distribution. Again, this is not for the raw scores. This is for once we've converted them to z-scores. Alright, that is it for this lecture. I hope it was helpful. Thank you, and I'll see you next time.